Okay. Now, since we have some time, let's take... This morning, 2 people were here in my first class, so I went through all the announcements, and then as more people came in, I thought, I need to tell them all this stuff again. So I waited till the end, and actually we had 100% attendance. It's a small class, but we had all 7 people were here, and I got to tell them all. My second class, there were like 2 or 3 people to begin with. I said, let's wait till, well, it didn't quite fill up, but more got here right at the end. Unfortunately, it was literally right at the end. I didn't keep track of time. They said, we're out of time and you need to tell us that. So that's why they were late leaving. And here's Ed. All right. So I want to tell you all the stuff that's going to happen toward the, at the end, but I really need to wait for more people to get here. So before we start the lab today, I will go through the whole spiel. So that's when I'll do the announcements and all that kind of stuff. Because I'm not sure everybody's going to listen to YouTube, so I want as many to hear that as possible. Okay. Now, if you remember on last Thursday, when we got to this slide, I looked in my book and I don't see tsunamis anywhere mentioned in this chapter. And so we're along about the bottom of page 623. That was the previous slide we did when we did longshore currents and rip currents and all that kind of stuff. So that's where this slide shows up here. So let's just do on tsunami and we'll move on from here. Tsunami is a Japanese word. It's basically the ocean wave created by an earthquake. And you say, how does an earthquake create an ocean wave? Well, an earthquake is a shaking or a movement of the Earth's crust, and if that crust happens to be under the ocean there, an oceanic crust, and it shakes it up, that creates a lot of energy. And that energy is transmitted to the water. It shows up as a wave and moves a direction away from the quake, and it's heading towards something else. Okay? Anything that's in its path is heading to. These can be and typically are the largest of the ocean waves. These are not waves caused by wind, by the spin of the earth, or anything else. They're caused by earthquakes. Okay? Now, a couple of notable ones. I think I've mentioned both of them before, but let's say them again. Sometime back around I don't know exactly the date, but I'm thinking it was around 1900 or so. I'm not certain on this because that's about the same time the big San Francisco earthquake was, and it would be sort of surprising if that happened in the same general period of time that this happened. What happened was a fairly major earthquake happened in Alaska. Okay, it, at least at that time, was the largest earthquake ever recorded. Now, there may have been 1 or 2 more major since then. I can't recall if there is, but that was a big earthquake. Okay? And it was not it was off the coast of Alaska. So it wasn't under land, the epicenter, and the focus was underwater. So I'm just going to make a guess. It was somewhere along here. It may have been along this part of the peninsula that Alaska takes, some of the coastline of Canada here. This part here, it could be on some of the islands out here. It was somewhere off of there. Really major, powerful earthquake. Now this may not look like far to you, but this is thousands of miles between Alaska and Hawaii. Alaska's in very cold northern climate, very warm tropical climate. The tidal wave that came out of that quake, the tsunami that came out of the quake, was big enough to do major, major damage in Hawaii, thousands of miles away. And again, it was back in the 1900s, early 1900s, late 1890s or something around there. And therefore, neither place was super populated. Alaska still isn't, but it's more populated than it was. And Hawaii was probably fairly well populated, but nothing like it is today. So it didn't do that much cost in human life or property damage, but it was a major, major quake. So that was one. That tidal wave tsunami traveled thousands of miles and still had enough energy to do a lot of damage. Okay. More recently, during your lifetime, and mine too, although I was born in the 1900s either, just off the coast of Japan, I'm pretty sure it's not on this map. The actual city is not on the map. The place is, I just don't know exactly where. I think it's this upper part of the island here, or here. I don't know which island it was, but on the west coast of Japan, there was a major earthquake. The tsunami from that earthquake came back toward Japan and completely swamped the coast. Okay. Now, Japan is a string of arc islands there, probably only been formed much more recently than most of the other landmass of the globe, because they come up recently. So you had no bogs and swamps and lowlands and stuff to collect fossil fuels for millennia, because it hasn't been there for millennia. So they have no fossil fuels in Japan. None. You know, no oil fields, no coal, nothing. So they had to import all of their fuel sources. So Japan, being pretty sharp people they are, and this is almost a little surprising after what happened to them at the end of World War II, but they decided to invest in nuclear power. And invest they did. They are almost totally powered by nuclear power. Okay? All their electricity, the vast majority of their electricity is nuclear. And of course, nuclear power requires water for a couple of reasons. Of course, one thing is to make water into steam. The steam is what turns the turbines. So you have to be near very good water sources. The other thing is the cooling of the reactors requires great quantities of water. And the third thing is heavy water, which contains extra hydrogen, extra neutrons in the hydrogen, deuterium and tritium. That's what controls the reaction. Okay? And they produce that from water. You know, they do centrifuges and stuff. Because a very, very, very small percent of water has that extra hydrogen with an extra neutron in it. So it takes a lot of centrifuging to get a little bit of water, of heavy water, and they're just constantly doing that. So all nuclear power plants are usually near water. They are. They've got to be. Okay? Now, most of the time, those are near rivers. But if you look how tiny Japan is, okay, and, you know, it's bigger than it seems here, but still, you don't have lots of long rivers there, and they're very heavily populated, so they can't afford to dam up that much river. So, you know, they use the ocean a lot for water, and they desalinate or whatever. And nuclear power has plenty of energy to do that. So they built most of their power plants right near the ocean. But remember, they're volcanic islands. They're on the Pacific Rim, the ring of fire. Maybe not the best place to build a nuclear power plant. but they needed the power, the energy to be an industrial economy. They needed that energy source. So, have you all heard of the thing Fukushima? That is the power plant, and maybe the town too, I don't know. I don't remember. It was somewhere in the northeastern coast of Japan. It was built right near the ocean. Well, the tsunami hit, the earthquake happened way underwater there. Tsunami hit, completely swamped the plant, knocking out power, okay, knocking down everything, and now the nuclear reactors have nothing to cool them, no pump to get water flowing through them, and they had probably the biggest meltdown that the world has seen since Chernobyl in Ukraine, the Soviet Union. I mean, that was devastating. Okay, that wasn't caused by a tsunami. This one was. Well, fortunately, the Japanese have built very safe plants. Not one that could withstand a tsunami, unfortunately, but very safe plants. So they had everything fairly well contained relatively quickly. An awful lot of radiation did splash back into the ocean, and there's hard telling what that's going to do to marine life there for centuries to come, you know. Maybe it'll moderate, I don't know. But the plant was destroyed, okay? And very, very major damage happened there, and that was caused by tsunami, the largest of the ocean waves. So what's the physical characteristics of tsunamis? This is hard to believe. They can come at speeds approaching 700 kilometers per hour. That would be about 420 miles per hour. I'm not going to outrun that. You know, in fact, it's going to be a very, if you're very close, like Fukushima was, there's no way that you can have enough warning to be effective at avoiding that at all. Lawrence here. Okay, the bottom part of the alphabet is doing pretty well. Top part's a little sparse still. Okay. Now, the wavelength. Remember what we talked about? Waves and wavelength. That's from peak to peak. 200 kilometers. That would be about 120 miles from this one to that one. Okay. And these are big waves. Remember, Jordan's here. By the way, the bottom part of the alphabet is doing incredibly well. Okay? Top part, not quite so well. Okay? So, what this means is, you're going to get hit by an enormously large ocean wave, and then 100, could be as much as 120 miles out, here comes another one. Just when you may be set. But, they're coming at about 400 miles per hour, okay, 420 miles per hour. That's flying. So you're not going to have a lot of time between those hits. That would be less than half an hour, maybe 20 minutes between them. Okay? And here's Chris. Okay. So, incredible. The wave heights are up to only half a meter. That's about a foot and a half, you know, about 20 inches in deep ocean. So if you're out in the ocean, a foot and a half swell or wave, it's going to be it's going to be very unusual because they're not usually that big out in the middle of the ocean, but you're going to weather it okay. But once they get into shallow water, they build because you see you got the wave energy coming in, lots of water here, not much place for it to go. It's got to go up. They get up to 8 meters, which is about 25 feet. That's pretty major. Okay, 8 meters, Remember this? I'm about 2 meters, the ceiling's about 3 meters, 8 meters would be close to the 3-story building. That water coming in, slapping you, you know, those most houses that would be on the beach, underwater, most 2-story buildings, underwater, 3-story buildings, maybe the very top wouldn't be quite underwater, but it's going to hit them hard. So you're talking about a lot of force, a lot of energy, a lot of devastation. Now, let me mention one more. Remember, for some reason I'm associating the two. I may be wrong on it, but it was within a year or two, maybe the same year, that the very major earthquake hit Haiti, and then just like a month or less later, one hit Chile. We talked about that back in the earthquake chapter. It was either that same year or just within a year or two of that there was another earthquake, this one beneath the water, off the coast of Indonesia. And here's Indonesia here. I don't know exactly where in Indonesia it was, but I think it was somewhere in this island here off the coast of it. And that tsunami hit, that earthquake hit, and the tsunami went 2 ways. It went back toward Thailand, and boy, did they get smashed. And it went across the Indian Ocean here, which is quite a bit of water that it transpired, and it smacked into southern India. Madras, it's now called Chennai. We have friends who that's their hometown, and then Sri Lanka, Alina's mom is Sinhalese, so her family is actually from there. She's dead now, but anyway, they got plastered by it, and many people died. It was a Sunday morning. They were out on the beach enjoying the water and the sand and the sun and stuff, and there was almost no warning. I mean, very little warning. Traveling those kind of speeds, it smacked, and it smacked pretty hard. Okay, now the good news on this, I think that's all that this slide says. The good news on this is that we have a great tsunami warning system now, basically because of that major one that hit in Alaska about the 1900s. Okay, when that hit, or sometime after that, they decided internationally we need to be able to warn people, and that we did. We have tsunami stations all over every ocean on the planet, and if a tsunami comes, one of these 0.5 meter or maybe even less wave, if it senses something very unusual like that happening, it sends a signal immediately. And not just some countries, every country in the world, especially that borders an ocean, has signed on to this, whatever the political is, however much they hate each other's guts, they all work together well with this. Our tsunami reporting system and our earthquake reporting system, both of those, the seismic system, they are well done internationally, probably better than anything else that man has ever done as far as cooperation. All right, so that's more than enough for tsunamis. Okay, the next thing is tides. Okay. And this isn't showing up here either. We talked about them in a previous chapter, so we'll just hit these pretty quickly too. These are, of course, produced by the Earth-Moon and Earth-Moon-Sun gravitational attractions, as we talked about back in chapter 16, I believe it was. The basic pattern is that you have 2 high tides and 2 low tides every approximately 24 hours. 24 hours and 50 minutes. Okay? 2 high tides, 2 low tides. So that means most days, will have 2 highs and 2 lows. Every now and then, the last either high or low tide will be right at midnight, and that means you'll have one more a little after noon the next day, but then you'll miss the one. So because of that 50-minute interval there will be a few days where you only have either one high or one low, but you'll always have two of one and one of the other, and it's very seldom you don't have two of each every day. Now these can produce strong reversing tidal currents in very narrow bays, okay? And there's a word for that. It's called a tidal bore. It's not what I'm doing to you now. No, it's a wave moving rapidly up a bay as the tide rises, okay? So this is the other source of some waves, and that's a tidal bore, which is a wave moving rapidly up a bay as the tide rises. Now, I remember reading a mystery book, may have been Elizabeth George, I don't remember which, and the unsolved, I think her hero is Inspector Lindley. I think this is one that he could not solve. Had a really good idea of what happened, but he couldn't prove it because twice a day, this area here under a narrow bay, when the tides came in, they came in suddenly, swiftly, and wipe things out. If you were out in the bay, which is largely sand, when they weren't coming in and didn't allow for it, it would beat you because you couldn't outrun it, okay? And the murder or the death, whichever it happened to be, occurred there. And they never could figure out if the guy just didn't know what he was doing, if it was suicide, or if someone set him up there. Because it took him away, there was no evidence produced. So, fiction writers have used this before, but they are pretty major. Most bays are not that narrow, and you don't have problems with it. But when you do have just the right geometry there, that tidal wave, that tidal bore could be pretty major. Okay? Now, we're finally back in the text. And this is ocean currents. This is at the beginning of page 624. Okay? What are ocean currents? Well, basically, it sounds so bizarre to talk about the ocean, an enormous body of water. I mean, capital enormous body of water with a stream through it. Okay, wait a minute. It's all water, but this is a stream transporting water over large oceanic distances, roughly along the same path, constantly. Stream running through. I mean, I picture a stream, something less than a river, just a little stream, moving along. But this is moving along in the ocean. Okay? It's produced by two effects. The first of these is a density difference in seawater. And basically, when you have density differences, those are predominantly caused by differences in temperature. Colder waters sink, have a high density, warmer waters are lighter, and they tend to rise. So that movement of water because of temperature, that's going to create some motion. We'll see a really good example of that coming up. Secondly, winds blowing persistently in the same direction. And we've talked about this before too, when we were talking about the fetch, the swells, and those kinds of things. And you've probably done this when you're playing around with stuff before. I can picture some of my nephews doing this. Getting a straw and blowing across the top of a glass of water. And if you blow just right, you can make some pretty good waves in that, and they can splash out really easily because you have winds blowing persistently in the same direction, moving the water in that direction, and that can create a current. Okay? So you have the different density differences and the wind currents, caused by current. Let's look at the density currents first. Okay? The denser water displaces the less dense water in deeper basins. So, picture this, folks. Let's take the North Atlantic Ocean. Okay? Where might we find some pretty cold water? Maybe coming off Greenland, coming up northern Canada, coming off Scandinavia. Really cold, dense water that's moving down. You have down here very warm water from the tropics, from the equatorial area. Less dense water. Okay? As this water is moving down, it replaces the warmer water on top, so the denser water displaces the less dense water in deep basins. Now, I said it's mostly temperature. There's actually three influences for density. The first is water temperature. The polar water is colder, therefore much denser than tropical water. The water in the tropics is warmer and therefore less dense. That's what I was just describing. Another, and this is not as major, but it is some, salinity. Okay, now can you remember? Salinity is the amount of salt per kilogram of water, basically, you're talking about. So, where there is more salt, higher salinity, you tend to have a little bit denser water. That's why salt water is denser than fresh water. That's why you float better in salt water. Okay? Now, where would you have buildup of salinity? Well, when you freeze water, it's just the water that freezes, not the salt, not the salines. So therefore, up in the northern area where water is freezing, okay, then the salt builds up there. So now we have another reason that northern water is very dense. Not only is it cold and dense, it's more saline and dense. Okay? Now, not the only reason though. You also have evaporation and runoff. Now these are two competing entities here. When you have water evaporating, again, that's only the water losing. So therefore the salt is building up. But guess what? Also where you have runoff, meaning say a river dumps into the ocean, to the bay, to the Gulf, or somewhere like that, that's fresh water. And now the salinity is much less. So right near where you have very warm temperatures, you have more evaporation, and it gets more saline, salinity goes up, but where runoff pours into a body of water, there you have less. So you have differences created there too. Denser because of more saline, less dense because of runoff, so you have motion going on there too. And then the third is suspended sediments. And again, this would be mostly where you have rivers dumping into the ocean. Because they don't just dump water, they bring along with it all sorts of sediments too. Remember, that's what makes your deltas, and those kind of things, the sediments falling out. Well, before they fall out, they are denser. So even though it's fresh water, less dense, if they have enough sediment in them, they're more dense. So again, you have competing things going on there. These produce turbidity currents to ocean basins. And you'll see this sometimes when you, especially if you look from up high down, you'll see, remember those longshore currents that run parallel to the shore? They could be turbidity currents because the stuff's coming in and that's creating a current there. Okay? Now, here's a picture of that first one. The cold, dense Arctic water that comes from between Greenland and Iceland, let's say, is coming down. And it's going downhill fast because it's very cold and very dense. That's Arctic water. Now, this is hard to believe. In between here, you have equatorial water, tropical water, very low density. So that's going up as this is coming in, Unbelievable. Now look at this. 30 degrees north, they claim that from way dense, here you have Antarctic water coming up. So you have Arctic water coming down from up here. You have the equatorial water that's really low density. And then from the Antarctica, hugging along the bottom of the ocean, you have that cold water that makes it up as far as 30 degrees north. That's where we live, basically. We're a little above that, up to here. So you have Antarctic water coming this way, Arctic water coming this way, warm water on top of both of those. Yeah, you can create some currents that way. I mean, you got a lot of motion going on there. Unbelievable, the amount of motion you have going on there. And guess what? We understand this about that much. We just discovered that those kinds of things can happen. Okay? And we don't know to what extent, how involved that is. It's just amazing how little we know about our oceans. All right, then let's look at the surface currents. These are the ones caused by salinity. The winds, the currents. I was back on density. The winds blowing persistently in the same direction. These are surface currents. These don't occur way, way deep. Wind doesn't have any influence there. Now, let me say this too. The deeper you go, the colder it is everywhere. Okay? I could not believe when the Gulf oil spill happened. Remember? That was what, maybe 10 years ago, or is it that long? I could not believe that, number one, the Gulf of Mexico was more than a mile deep. I did not know it was that deep. And down there, when you're more than a mile deep, absolutely no sunlight makes its way anywhere close to it. And by that time, the waters are freezing. Not making ice because they're too dense for that. They have too much salt in them for that. But they're very close to 0 degrees Celsius, 32 degrees Fahrenheit. And that's what made repairing that spill so difficult. Number one, more than a mile down. Number two, extraordinarily cold. And number three, the pressure. Because you have a mile of water on top of you. And every 10 meters, 10 meters, which is about a 3-story building, every 10 meters adds another atmosphere of pressure to the water. So the pressure we feel right here, which you don't know you're feeling, but it's there, that's one atmosphere of pressure. 10 meters beneath the surface, you have another atmosphere of pressure. 10 meters below that, another one, another one. And guess what? A mile is about 4,000 meters. Isn't that right? The 4,000 meter run in the Olympics, I think, is a mile. So that's 40 more atmospheres of pressure. So you got, that was a very hostile work environment trying to repair that from a distance. You couldn't get down there. Okay, so the surface currents are only at the surface. That's where winds affect. Okay, the global circulation patterns are maintained basically by the patterns of prevailing winds. And over the oceans especially, the winds tend, you don't have anything to block the wind. So wherever the winds are coming from, they usually always come from there. Now, they're also influenced by the rotation of the Earth and the ocean basin shapes. We saw that with the deep ones too. The deeper you go, you can have a lot. In fact, you know where the tallest mountain ranges in the world are? Would you say the Himalayas in Nepal? No, in the bottom of the ocean. There are mountain ranges way taller than the Himalayas, but they're so far down they don't even come close to the surface. You're talking about a great deal. So, any of that shapes down there, they can make the currents do really strange things. Now, here's a couple of words. I don't know if you'll ever use them again. I'm pretty sure this is called a gyre. G-Y-E-R-S, gyres. great systems of water circulation centered in the mid-latitudes. Now, mid-latitudes, that's where we live. That's between the tropics, 23.5 degrees north and south, and the Arctic circles, an Antarctic circle, which is 66.5 degrees north and south. So in this region here, you have these big patterns, great systems of water circulation centered in those mid-latitudes. The direction is dictated by the Coriolis effect. Remember, that's the combination of the spinning of the earth and motion up and down. That's what creates tornadoes. That's what creates hurricanes, okay? Thunderstorms, that rotation, okay? So that's the Coriolis effect. A good paper topic, by the way, and we'll get on to that in a minute. Okay. Now, here is a map, and it's in your text also, of some of these surface currents. And you see there's some major ones. The one that we're most familiar with is called the Gulf Stream. And it shows it circulating like this, but you see some of it comes from here. It's not all from the Gulf. It's also from the tropical waters of the Atlantic, and it comes around and basically warms our entire eastern seaboard. I mean, keeping it nice and toasty. That's why you can have beaches at New Jersey and Long Island, and people love it. I mean, it's warm. It's very pleasant because of the Gulf Stream. Keeps it warm. That's warm ocean currents moving up. That's why England was able to be queen of the ocean. That's why her fleet was never blocked by ice, because the Gulf Stream kept that. Well, look how far North Britain is. Way up there. There's the Arctic Circle right there. So they're way up there. We're over here in Nova Scotia, which is actually further south than they are. They freeze up every winter. But Britain doesn't. Why? Because you have the Labrador currents coming down here, chilling this like crazy, whereas the Gulf Stream is moving like that, keeping Ireland, maybe not all of Scotland, but England, pretty much free of ice. Okay? Poor old Baltic here, they don't have that Gulf Stream making it in there. These places are frozen solid in the wintertime. And here, Britain is the same latitude, and they're perfectly free. Okay? So there's one of the most famous, the Gulf Stream. Now, over on the west coast, this is what's really bizarre, you have a North Pacific current coming in. As part of this goes down the coast, bringing cold water, Arctic water, down here to San Diego. You have to have wetsuits on the beach there in the summertime. New Jersey, maybe trucks. Okay, I mean, you don't need any wetsuit at all. Long Island, you don't, because you got the Gulf Stream warming this, the Pacific current chilly, San Diego. Okay? Now, but the same North Pacific currents coming in here that cool it down here, they swip around and keep it warm in Alaska. Because warm for Alaska is chilly for San Diego. Very much so. So it's pretty bizarre. Notice here some of these currents here coming up near Antarctica there. Now these are surface currents, but you can just easily imagine the density currents that are way down deep probably follow some of the same patterns making their way up here. So you have all of these currents, equatorial currents, and notice most of the equatorial currents are moving west to east, and that's because it just seems like most of them are. But that doesn't, I can't explain that. These I can explain. These up here, I really don't know why they're moving in that direction. I understand this, yeah. These coming in this way. But see, the Atlantic things get really mixed up here because it's a really fairly small or narrow ocean. The Pacific is so huge, that basically you have almost a clockwise flow in the northern hemisphere, going clockwise in the northern hemisphere. In the southern hemisphere, it seems to be going more counterclockwise. And that's probably Coriolis effect. Okay? That would kind of make sense. Okay? Whereas the Atlantic is trying to do that, but things just get in each other's way here pretty badly. This appears to be going counterclockwise here, a little bit clockwise here. Okay? So, all these currents, and many of them have names: the Peru current, the Falkland current, the I can't read all the writing. South equatorial current, North equatorial, or whatever that is. I think it is North Pacific current. I mean, you just have the tons of them up there. The Labrador current, I can't read all the names here, but they're just all over the place. Okay, here's the Liddell current. I think down here. We saw the Liddell Ocean down there too, or sea, or bay, or something. Okay, so there's your surface currents. And one of the last things that we're going to hit here is the ocean floor. Before we do, there is a person behind the science, pretty impressive character. Her name was Rachel Louise Carson. Now, she didn't live a super long time. It looks like just 57 years. But she was a U.S. biologist, conservationist, and campaigner. Her writings on conservation and dangers, hazards of many modern practices, she was way ahead of her time. Quite a visionary. And it was fairly unusual at that time for have a woman who was that strongly voiced, you might say, and able to do this. So I'll let you read that. If you do choose to write on her, this cannot be your source. This can give you the idea, but you'll need to find your source elsewhere. Okay? So now let's move to the ocean floor. Ooh, that's a long way to go. And this is the last section, and it's not going to take long. Okay? Now, the ocean floor has made up of several features. And I think probably the slide will help you see these features a little bit. The first we have the continental shelf. Now, here in the U.S., this only occurs on the Atlantic side of things. You don't have a continental shelf to speak of on the Pacific. The Pacific goes right down into the ocean almost, okay? Whereas the Atlantic has a big, broad, long continental shelf. And what this is eroded continental margins. Now, what do we mean by that? Well, probably at one time the continent came up here, but it's eroded away and part of it went down below, so it leaves a shelf here that is now shallow water, okay? Now this is great when you're swimming, okay? You can go way out there and still be standing up. Be careful, because currents can be coming in. It's lousy if you're doing shipping, because that means you have to dig a trench through that to get in port, okay? So there's pros and cons to it, okay? It's relatively shallow water. Now, not always shallow enough for you to walk on, but quite often it is. Now, what you have after that is a continental slope. That is probably the original edge of the continent, and that falls off pretty quickly. On the west coast, that is the edge. Yeah, I mean, it goes down and goes down really, really quickly. Okay? Steeper is a transition feature beyond the continental shelf. It's often cut by submarine canyons. In other words, they don't really show any here, but you have gouges in them. You know, you have a shelf here, but then you have a deep canyon that probably, currents or other things have washed through there and washed it out, eroded it away, much like water does on land. It was probably softer soil or rock material there. So often cut by submarine canyons. Now, then you have what they call the ocean basin. Okay, there it is. Ocean basin floor. Okay. Now, this is usually the deepest part of the ocean on average. It's characterized by practically perfectly level abyssal plain, and here they show this. This is ocean basin floor. This is abyssal plain. Those are the same type things. Okay, nothing too unusual there. Now, you can also have these mountainous regions in there, in the middle of the plains. They don't show it here, but they show it down here. Here you have seamounts. Now, this is your Rift Valley. That's a big one in the middle of the Atlantic, but you'll see there's other places that occur as well. They didn't show many here, but these could be seamountains down here as well. Okay? Now, the very deepest part, the ocean basin is typically pretty deep. But when you have the trenches, what creates the trenches? Do y'all remember that? The oceanic plates subducting under either the continental plates or other oceanic plates. And where that goes down, you have these trenches formed. Now, that's what our Pacific thing is. It basically is more like this. If there's any continental shelf there, it's very little. Okay? In fact, most of the time not. It goes straight down almost into a trench. There's a little bit of a slope there, the continental slope, but it's going right down into a trench. The Atlantic does not have that. The Atlantic, remember, is being spread apart like this, and so there's no subduction going on here. That's all over in the Pacific. Not all, but mostly in the Pacific. Maybe on the eastern side of the Atlantic they may have some, but on the western side, no. Our Atlantic coast and the Gulf of Mexico looks more like this. If anything, along the continental shelf. Okay. And then you have the volcanic peaks. These form your arc islands, for instance, like the Hawaiian Islands. These are seamounts that actually break the surface. Okay? Hawaiian Islands, Iceland is a volcanic mountain. The island of Japan, the nation of Japan, volcanic islands. Okay? Most of the Pacific islands, the Marianas Islands, the Caledonian, all of New Zealand, those are all volcanic peaks scattered, forming scattered seamounts across the bottom of the ocean. And these don't always occur on what's the word for it? Plate boundaries. Hawaiian Island's right out in the middle of the Pacific. It's just a weakness in the surface, the basaltic rock there, a fracture or something like that, where the volcanic material comes to the surface. Okay? But quite often they are on, like Japan and Aleutian Islands, they are on the boundaries of the plates. Okay. Now, this shows some of the trenches. The other show the current, this is the trenches. And it's not just the trenches, but also the ridges. Now, we talked about the Mid-Atlantic ridge there. Iceland is right on it because it was formed by it, okay? And it goes down pretty much the middle of the Atlantic Ocean. But then there's also a ridge between Africa and Antarctica that continues here. And between Africa and Australia here. And between Africa and India there. Okay? These ridges occur here where you have diverging plates. Okay? Remember, this is the Indo-Australian plate here. That's the boundary, and the African plate here. So that is separated by a ridge, just like the Eurasian plate and the African plate are separated from the North American plate and South American plate because there's a divergence there. Now, believe it or not, the Pacific also has ridges. Here's the Mid-Pacific Ridge, where you have some splitting. The Hawaiian Empire, I think is what this is called. That's why the Hawaiian Islands are there, because it's actually a small diverging area there. It doesn't separate plates, but it's a diverging area. Okay? So you have those ridges all over the globe. You also have the trenches. Now, most of the time the trenches are along the boundary of plates, okay, where the oceanic plate is subducting under the continental plates most of the time, but it can be oceanic plates as well. So you have a trench in the Aleutian, following the Aleutian Island terrain. Trench there. Trench over here, I can't even read it, but you can read it in your book. This is the Peru, it doesn't say Peru, Chile, I guess it is trench. Here's the Middle America trench. Aleutian, we mentioned Puerto Rican trench. It includes Puerto Rico, Hispaniola, and part of Cuba. There's a trench there where the boundary between the Caribbean plate and the Atlantic North American plate are. Over here, of course, you have these island chains. You expect to see trenches. There's one, I think that is Sundra. I can't read it well. There's tons of them. Here's looks like the Mindanao trench. The big island in the Philippines in the south is the island of Mindanao, so that's the Mindanao trench. I wish they showed this better. Of course, you have a trench off Japan. That's probably where the earthquake occurred that spawned the tsunami. This is more of the Aleutian trench here, I believe. I can't believe they don't show this better than this. Oh, there it is. The Marianas Trench. That is the deepest part of any ocean anywhere. And I can't remember how many miles deep that is. That is really, really deep. The Mindanao Islands here include the island of Guam and other islands in that, Marianas Trench. Marianas Trench. This one now, Marianas Trench is here. That's the deepest one in the globe. Okay? That's it, folks. That's the last slide at the end of chapter 24. And you know what I'm going to say next, right? Nothing replaces reading the chapter. As you've seen, the slides are a little behind the book, and so the book has a little more recent material, a little more up-to-date material than the slides ever will. The summary here is fairly short for this chapter. There are some that are longer. There's quite a few words, mostly in italics here, that are important. You'll see those as the key terms over here to the right of the summary. They're listed alphabetically, but the page number on which they're first located or defined are given there. And then the very best thing to study for your test is the applying the concept, in my mind anyway. And there are only 46 of those questions, which is way more than you're going to have on a test. And these won't be the same questions, but they're covering the same type of material. So anyway, that's going to be a good thing to study. It's a little bit shorter than most have been. Then we have questions for thought. And by the way, the answers are given here too. Questions for thought, there's only 13 of these, maybe a little bit shorter than most. For further analysis, 6, which may be a little longer than most. But all those are good questions to look at. And then the parallel exercises, some of these are a little much of a stretch. So I'll let you decide whether you want to do those or not. Okay. You're not going to have that much calculation to do in this chapter. All right. Any questions on that? Okay. What I'm going to do here, because I really don't think there's anything else that I can show you. Does everyone have a book or have access to a book? Some neighbor or somebody there. Let me go back and just remind you that last slide that we saw of the trenches and the ridges, that's on page 627. You'll need that for your lab today. The earlier figure 2422 on page 625. You'll need that for your lab today, the currents. And, let's see, trying to think what some of the other features are. Sort of the one on 2412, figure 2412 on page 618. You'll probably need to pick some of the things out of that one when you're talking about bodies of water. And then the rest of them pretty much I think we've got covered. Okay? So any questions on chapter, this is hard to read, put up here, much easier to read from a book. That's why I say if you have access to a book, I think it'll be a lot easier than trying to read it off the screen. Okay, so if no one thinks you'll need it, I'm going to shut this down so that it can be uploading. Is that all right? All right, so I'm going to pause it for. All right, what we're doing now, I've passed out lab number 9, which is, and this really isn't number 9 because we didn't get to go to planetarium. That would have been 4, I believe it was. So since we didn't get to go there, this is really for us, lab number 8. But it's on Earth's Waters, chapter 24. Everybody did get a copy of the lab, right? Okay. The first question is on the early part of the chapter, under the section called Freshwater into Surface Water, and I think you'll find a pretty good figure in the book that will help you answer this, the 3 major watersheds in the continental U.S. And then the next part is mostly taken from there on, is taken from the ocean, which is the last part of the chapter. There's seawater, but that's not really talking that much about that. It's the oceans, which is toward the end. So there's a lot in the middle that's left out, so that was hard to come up with a good lab things for. So the ocean basically begins, I know it was in here because we did it today, and I can't see it. Well, but it's under seawater, okay, in that. So,
617.
Second?
617.
617. You're probably right. I must have just. Yeah, oceans and seas. Yeah, it's under 24.2 seawater. There it is, oceans and seas. So most of what you need for the rest of this, you can find from that section on. Okay? Now, again, some of your figures I think will be helpful for you. And it says, name the 3 largest oceans on Earth and list 2 continents that border each one. Now remember, a continent is a large land mass as opposed to a country, which is much smaller. So these are asking for continents. Okay? Now, the next question, number 3, and off that same figure that you see that you could use for the oceans, you can find 8 major seas. Now there's more than 8, but there's at least 8 listed there. And then it says name a country that borders each sea. Now there I'm looking for countries, not continents, okay? And I have students mess up on that quite a bit too, so I'm looking for countries there. If you need to use the globe, it's up here. And you can find countries that border those various seas. I only need 1 country. For the oceans, 2 continents. For the seas, 1 country. Okay? Then the next one is asking about ocean currents. So you have to go through a bit later in the chapter. In fact, it's several pages over, and you'll find a figure that talks about the ocean currents. And it shows tons of different currents. Okay? It says name 10 of those ocean currents. So 5 are on the front page, 5 are on the second page. And it says list the ocean in which each of those is associated. Now you might have some that are called the same names, so be sure you list which ocean you're talking about. Okay? So those are the ocean currents. Number 5 is name 4 of the larger ridges, and that's that last slide that we saw. Larger ridges on the ocean floor and the ocean in which that ridge is associated. Okay? And by the way, you're going to use the same ocean names over and over. And then name 12 of the larger trenches, and that's on that same figure with the ocean, with the ridges. Name 12 of the larger trenches on the Earth's ocean floors and the ocean in which each is associated. And those are pretty specific, which one, and you pretty easy to figure out which ocean each of those belongs to. Okay? Are there any questions about the lab? Okay, take a look at it. Take a look what it's asking, because I sort of want to go on and shut off the screencast-o-matic so it can start loading. So are there any questions? All right. We'll get started then. If you have any questions, please ask. Don't hesitate to ask questions. And by the way, folks, you're going to have plenty of time today, so if you're behind in a lab or a test, and that's what Jessica was asking about, if you're behind in a lab or a test, this is a great time to make it up. We've got plenty of time today. Because guess what? Thursday, beginning of class, okay, it depends on where we are. If we're on the field trip, it'll still be probably at the beginning of class, or it'll be right at the end of sometime. I'm going to return everything to you. That means I cannot accept another test or lab after I return these. This class has been pretty good. I think you've gotten like 3 tests back and 2 or 3 labs. Okay? So you've been doing better than most classes have, but still toward the end, I'm missing a lot. So if you don't get them in now, and guess what? If we don't go on this field trip, we missed the first field trip, so guess what? We only have 1 lab you can drop. Because field trips, we're going to give you some bonus labs. We don't have them this year. Okay, so let's do it. All right. Any questions?
So I'll take one question. So Thursday, we just supposed to go on the field trip?
Okay. Okay, yeah. Okay. I guess this is the best time for this. Before I shut this down, I was going to wait to see if a few more people showed up, but so far they haven't. All right. I already started this with first thing Thursday. Okay, today we finished chapter 24, and we're doing the lab for 24. That means on Thursday, there are some possibilities. I'm going to check my email while y'all are working on your lab to see if Jerry Tracy's responded yet. Okay, I'm not holding my breath, but hopefully he has. Okay, I should be able to let you know before it's over today. In fact, I may put this on pause so I can check the email and come back and make the announcement on Screencast-O-Matic, and it'll be on YouTube. But we might go to channel 13. If we do, my guess it'll be later in the period, okay? Because Jerry doesn't usually get in early. Somebody else does the noon weather. He does the evening and late night weather. So he starts his 8-hour day pretty late in the day. So my guess is we may not leave here until 2 or something like that. I haven't thought through it to see for sure. But anyway, we'll figure it out when we find out whether we're going or not. But anyway, I think that'll be the late part. So we'll have time on Thursday for me to give back all the labs and tests that have been done, and after that you can't make up anything else. And then the other thing we need to do Thursday, if we have time, is do the test on chapter 24. Now, if the field trip's going to eat up just about all the time, then on the following Tuesday, when we would have our final, you'll just have 24 tests and the final. 24 tests is not going to take you more than 30 minutes. The final probably won't take you 15. So you can easily fit them both in next Tuesday if we go on the field trip on Thursday. Does that make sense? So we'll see. I just won't know. But if we don't go on the field trip, all we got to do on Thursday is you turn in anything, bring it with you that you haven't done, and we'll do the test, and then you get to go home early. Sorry about that. Cheat you out of your tuition dollars. Okay, but we finished everything. So, except for the field trip. And so we missed it. The final will be the following Tuesday. What's that?
The final, It's just, we have a study guide or?
Okay, the best study guide for your final are your tests. That's why I'm giving them all back on Thursday. And basically your final is going to be, the tests have been mostly multiple choice with a few fill in the blank. The final is going to be matching. About 20 questions, it seems like. And I'll have definitions, descriptions on one side of the page, and then the words that match those on the other side with a blank. And you'll get put in the letter for this that matches the word over there. And that's what I'll be doing. So it's going to be a pretty easy test. It'll be like the top 3 or 4 concepts in each chapter. That's what I'm going to go for. Yeah, Lauren, did you have a question? Find what? Okay, number 2 was what? That's the 3 largest oceans. Well, it's written in the text, but then there's also a pretty good map of those oceans. Okay. You can see, okay. Okay. The words are on page 617, and the picture, the graphic, is on page 618. Now, it doesn't list the continents. You need to know that, but I think the continents are all listed on the globe. Okay? Yeah. What's the continents? Yeah, listed there. You can take it, handle it, whatever you do. Okay? Good question. All right. So did I finish that? Okay. I think that covered everything. Oh, the only other thing is, do you want to plan for the pizza to be no, we don't know about the field trip. Let's plan for the pizza to be Tuesday when the final is. And does anyone have any dietary restrictions on pizza? You don't eat meat? So I'll have at least 1 cheese pizza. Any others? Okay. You want pepperoni? Okay.
What about drinks?
Okay. You provide your own drinks, okay? Non-alcoholic. Okay. Oh, yeah. Okay. No mixers. Okay. Now, the other thing with that is how many do you think we need? I'm talking about Little Caesars because it's the closest place I know of. Okay. About how many of those would you think we need? 13 people in the class. 2 pepperonis. At least 1 cheese. Any others? Is 3 going to be enough for everybody? There's about 8 slices per box, so that would be 24 slices. We have 13 people in the room if they all show up. Huh? Okay, so 2 pepperonis and 1 cheese. Okay, but y'all can share and do others. Just don't all of you eat all the cheese and not leave any for Chris here. Okay, so I'm going to put this back on pause